Good afternoon to one and all. This session will be taken by Mr. Pradyumna Kumar Behera, Research Scholar at NIT Rourkela. He is working under the supervision of Professor Monalisa Patnaik ma'am. He will take the lab session on the topic Development of Wind Turbine Emulator for Wind Energy Conversion System. Mr. Pradyumna Kumar Behera received M.Tech degree in Electrical Engineering from Bir Surendra Sai University of Technology, Burla, Odisha in 2016. He is presently pursuing his PhD degree in Electrical Engineering at National Institute of Technology, Rourkela, India. His area of research interest include design of power electronics converter, renewable energy system, hybrid energy storage system, electric vehicle charging infrastructure, and power management of DC microgrid. Now it is over to you.
Thank you, Anindya, for the introduction. First of all, I would like to express my sincere thanks to Professor Prabhat Kumar Rai sir, Professor Monalisa Patnaik madam, and Professor Arnab Ghosh sir for giving me an opportunity to share my ideas in this 5-day short-term course, Sustainable Technologies and Energy Management of Hybrid Microgrid, STEMM 2023. And a warm welcome to all the participants from different parts of the country. Now I will share my screen. The title of the presentation is Development of Wind Turbine Emulator for Wind Energy Conversion System. These are the learning objectives. The first objective is modeling of wind turbine and study of various wind turbine characteristics. In this, we will try to understand the need for emulating the wind turbine behavior. Along with that, we will model the wind turbine emulator. We will model the wind turbine with static and dynamic characteristics. Next, we will study the feasibility of DC motor to imitate the wind turbine characteristic. Here we will see whether there is some analogy between wind turbine and DC motor is there or not. So the analogy between the wind turbine and DC motor will be focused here. Next, we will discuss about the choice of generator for the wind energy conversion system. Here we will have a brief discussion on the self-excited induction generator. And finally, we will discuss about the real-time implementation of wind turbine emulator coupled with the self-excited induction generator. Here, all the hardware components involved in the system will be discussed along with the current sensor design, gate driver design, and the interfacing of DSpace digital controller with the developed plan. Along with that, I will give some basic introduction of the control desk 5.6, which is basically used for plotting and measurement of real-time data. Let us look into the introduction first. At present, owing to the depletion of various fossil fuel reserves and concern about the environmental pollution, the renewable energy sources are being utilized to meet the ever-increasing load demand. Among various renewable energy sources, wind energy is Hello. Among various renewable energy sources, wind energy is considered as a potential source of clean energy for a sustainable future. So various research works are going on to develop a reliable control strategies, optimization technique, forecasting methodologies to get optimum power and reliable operation from the wind turbine. However, it is not feasible to bring or install such a big wind turbine in a laboratory for research purpose. Hence, the design and development of wind turbine emulator becomes vital for a wind energy conversion system. So let us understand the importance of wind turbine emulator. This wind turbine emulator can imitate the working of a real wind turbine and its complete characteristic to help students and researchers to get practical knowledge about it. Further, repeated laboratory type interactive education at on-site wind power plant is often impractical. So the development of wind turbine emulator as a test bench can work for a trial and verification of various power electronic converters, wind turbine generators, and can be used to implement various control techniques. The system configuration that need to be emulated to interpret the behavior of the practical wind energy conversion system is shown in figure 1. You can see it includes the DC to DC converter fed separately excited DC motor. This one is our DC motor. It is coupled to the self-excited induction generator, and at the stator terminals of the self-excited induction generator, a capacitor bank is connected. And the output of the self-excited induction generator is fed to a three-phase rectifier and finally connected with the load through a single pole double throw switch. You can see here, this arrangement is basically a step-down chopper which is feeding power to the DC motor. Now I'm going to discuss about the modeling of wind turbine. First of all, I will discuss the static characteristic, and after discussing the static characteristic, we will discuss about the various dynamic characteristic involved in the wind turbine modeling. Basically, the kinetic energy of wind having a velocity v for an air sample of area A that is basically perpendicular to the wind stream and having a thickness dx that is basically parallel to the wind stream is given by half mv square. So basically the air density is rho equal to m mass upon a dx. This a dx is volume. From here we will calculate the mass. So we will get the equation 1. So the kinetic energy will be half rho a dx into v square. Next we will try to find out the power contained in the wind. The next equation, equation number 2, determines the power contained in the wind. The power contained in the wind is basically the rate of change of kinetic energy. So if we differentiate the equation number 1 with respect to time, then we will get power contained in the wind, that is half rho a v cube. However, it is not possible to extract 100% power from the wind. So a parameter Cp is introduced, which basically represents the conversion efficiency of the wind energy to mechanical energy. It is otherwise known as power coefficient of the wind turbine. The parameter Cp is function of tip speed ratio, that is basically the ratio of linear velocity of blade tip to the wind velocity and the pitch angle. The output mechanical power of the wind turbine is basically half rho into Cp A into V omega cube. This is one important equation which will be used while modeling the wind turbine. The tip speed ratio is basically the ratio of linear velocity of the blade tip with respect to the wind velocity. So it is given by the rotor speed or the angular speed of the blade into radius upon the velocity. And the parameter Cp is a function of the tip speed ratio and pitch angle, which varies for different types of the wind turbine. And the parameter Cp represented in equation 5 will be used for the wind turbine modeling along with equation number 6. The various coefficients C1 to C6 are given here. You can see. One more thing to notice that this tip speed ratio is a dimensionless quantity, because it is basically the division of linear velocity of blade tip with respect to the wind velocity. So the mechanical torque generated is given by output power or the output power of the wind turbine upon the angular speed of the turbine. So here we get 1 by 2 lambda rho Ct lambda comma beta pi r cube v square. The various power curves of the wind turbine are displayed that demonstrate how the amount of mechanical power generated by the turbine depends on the speed of the rotor. We can see at every wind speed there exists an optimal turbine speed that basically enables the extraction of maximum power at the shaft. Here various plots are given. Figure 3 represents the power versus speed characteristic for different wind speed. We can see that as wind speed is increasing, the power output of the wind turbine is also increasing. Next is the torque. Figure 4 shows the torque versus speed characteristic for different wind speed. Here the same thing is happening. We can see that as we are increasing the wind speed, the torque is also increasing. The figure 5 represents the pitch angle versus tip speed ratio for different pitch angles. It can be seen that Cp decreases with increase of beta. if we are trying to increase the pitch angle, then the power coefficient is reducing. So what conclusion here? One conclusion we can draw that the extracted turbine power can be reduced by controlling the pitch angle. Till now I have discussed the static characteristics of the wind turbine. Now I would like to discuss the dynamic characteristic of the wind turbine. In real world, the wind speed varies with altitude, which means that different parts of the wind turbine are exposed to different wind speed. The top blade will experience high pressure from the wind, and the lower blade will experience less amount of pressure. So this phenomena will create a shearing force on the turbine blade, which can basically affect the power production and cause wear and tear of the blade as well as the entire wind turbine. So we need to model this characteristic into our, we should consider this dynamic characteristic into our model. Next is the turbine shadow. When the tower hub of the horizontal axis wind turbine blocks the wind flow, it basically reduces the wind speed, and that basically affects the torque output of the wind turbine. So when these two factors combine, they cause oscillation in torque and power output that have a fundamental and a third harmonic component. The fluctuation in output power are directly related to the rotational frequency of the blade. Suppose we assume the rotational frequency of each blade in a wind turbine is P, and there are 3 blades, then the total fluctuation will be 3P. This phenomena is commonly known as the 3P effect. So it is expressed in equation number 8. Furthermore, the output torque of the wind turbine is reduced due to the inertia, which causes slow variation in the shaft speed compared to the sudden changes in wind speed. So in order to ensure optimal torque, a compensating torque is introduced to overcome the inertia effect. The compensating torque is expressed in equation number 9. So the dynamic equations can be combined with all the static equations to form the complete torque equation that basically governs the behavior of a practical wind turbine. The figure 6 represents the block diagram of the wind turbine model. It is simulated in MATLAB Simulink and implemented in the DSpace control desk for real-time interface. The input parameters for the model are the shaft speed, the wind speed, and the pitch angle, while the output is the reference armature current. Now I would like to discuss the wind turbine emulator using the separately excited DC motor. To emulate the wind turbine characteristic in a DC motor, it is very important to study the power versus speed characteristic in a real wind turbine as well as the DC motor. The equivalent circuit of the separately excited DC motor is shown in figure 7. The DC motor voltage, back EMF, electromagnetic torque and power are given in equation 10 to 13. All these equations are already known to us. So if we are neglecting the losses, the power output of the DC motor is equal to torque into the rotation angular speed of the motor shaft. So here, putting all these equations together, we can calculate the electrical power output of the motor, which is basically dependent upon the terminal voltage and the angular speed of the rotor. So suppose we keep this armature voltage, means the terminal voltage of the DC motor as constant, we can see that the relationship between the power developed by the DC motor is a conic function of the angular speed of the shaft speed of the DC motor. So the DC motor power versus rotor speed curve with different armature voltage is plotted in figure 8a. And the wind turbine power versus rotor speed curve with different wind speed for a wind turbine is plotted in figure 8b. From these two graphs, we can see that the shape of the both of the curves are quite analogous to each other. Therefore, the wind turbine power curve with wind speed variation can be obtained by varying DC motor armature voltage. Next, I am going to discuss about the control of the wind turbine emulator using DC motor using a PI controller. Basically, you can see this is our wind turbine model. Here, the inputs are wind velocity, pitch angle, and the wind turbine angular speed. And the output can either be torque or power. In this emulator, we have considered torque as the output of the wind turbine model. So the DC motor speed is controlled by regulating the armature voltage to imitate the wind turbine characteristic. The shaft speed of the DC motor is measured using a quadrature encoder, that is a HEDM 5645 quadrature encoder, and the input through the incremental encoder interface is given to the DSpace DS1103. For a particular wind speed and pitch angle, the output of the wind turbine model gives the reference torque. So the output of the wind turbine model is basically the reference torque, which is further divided by the torque constant and the gear ratio to generate the reference armature current. This reference armature current is tracked with the actual armature current of the DC motor and is processed through a PI controller to generate the duty cycle for the step down chopper, or we can say for the DC to DC converter used in the setup. So that the error output is basically given to the PI controller to produce a controlled voltage for driving the MOSFET. The switching frequency considered here is 5 kHz. The schematic diagram of the wind turbine emulator setup with digital input-output interfaces through the DS1103 ADC channels and DAC channels is shown in figure 10. We can see this DSpace CLP1103 interface is basically acting. This is basically having 20 number of ADC channels, out of which 16 are multiplexed analog to digital converter channels and 4 are parallel processing analog to digital converter channels. It is having 8 numbers of digital to analog channels, and it is acting as the interface in between the host PC and the actual plant. So the modeling of wind turbine emulator and the controller implementation is done in the MATLAB Simulink, and the control desk DSpace control desk 5.6 is utilized for experimenting, and it is basically a visualization software. It is also utilized for data monitoring, data recording, storing, and plotting. We can see here only one current sensor is used. We are sensing the armature current, and it is fed to the ADC channels of the CLP1103 interface, and it is sent into the and it is converted into digital signal and sent into through the communication bus of the DSpace CPU. And the PWM output for the wind turbine emulator is fed from the DAC channel at a frequency of 5 kHz to the switch, to the MOSFET. The experimental setup of wind turbine emulator is shown in figure 11. And next I will discuss about all these hardware components involved in the system. These are the specifications of the wind turbine as well as specification of the DC motor SCIG set. The cut-in wind speed considered for this wind turbine is 4 meters per second, and the rated wind speed is 7.5 meters per second. The turbine radius is considered to be 1.25 meter, and the rated power of the wind turbine is considered as 500 watt. Next, I am going to discuss about the hardware components involved in the wind turbine emulator setup. So I will be using one by one approach to discuss all the components involved in the system. The first component is the power MOSFET. The IRFP 460 is used as a control switch. You can see the pin diagram is shown over here. all are acquainted with the pin diagrams of a MOSFET. It is basically having three terminals. First one is the gate, second one is the drain, and third one is the source terminal. For your quick reference, I have given the drain to source voltage, that is VDSS, is 500 volt of this MOSFET. The gate to source voltage of this MOSFET lies in between plus minus 30 volt, and the continuous drain current is 20 ampere. Next, we will discuss about the power diode. This power diode is used for the freewheeling action, and the pin configuration, you can see it is basically a MUR 460 diode. It is an ultra fast recovery diode with a maximum reverse recovery time of 75 nanosecond. So this will be utilized as a freewheeling action during the turn off period of the pulse signal. During the turn off period, this diode will provide the freewheeling action of the inductor current. Next is the bypass switch. Here a single pole single throw type bypass switch is used, and it is playing a very important role in the wind turbine emulator setup, because during the starting the motor speed will rise from 0 to a certain value. So at that speed the power developed by the wind turbine model is 0, which causes the reference torque to go out of range. So as we know that the turbine torque is equal to what? Power output by speed of the rotor. So if the rotor speed is 0, so the reference torque will become too high, so it will go out of range. So therefore the switch S is used to bypass the power MOSFET for some duration initially, allowing the motor to gain 50% of the rated speed. Thereafter what we are doing, we are basically opening the switch, and the PWM signal from the control drive is given to the power MOSFET to regulate the armature voltage. Next is design of the current sensor. In this we have used a Hall effect current sensor, that is LEM make LA55P current sensor we have used. This sensor has a maximum current measurement of 50 ampere, and while developing the test rig, we have used this current sensor to scale down the current from plus minus 10 ampere to 5 volt. So which gives the sensor gain to be 2. The sensor gain considered here is 2. So you can see the number of primary turns must be selected such that the measuring burden resistance ROI falls within the range of 50 to 160 ohm. This is basically specified by the manufacturer datasheet. Further, the number of turns in the primary winding is basically decided by the maximum value of current to be measured. Means we can decide the number of turns in the primary side using this equation. This is the maximum current rating of the LEM current sensor, and maximum current which I want to measure, that is 10. So if I am trying to measure a maximum current of 10 ampere, then my number of turns should be equal to 5, or it can be less than 5. And this current transducer exhibits a conversion ratio of 1:1000. So for a 5 turn and 10 ampere current, the output current will be I naught equal to Is into number of turns by the conversion ratio, which comes to be 0.05 ampere. So for an input current of 10 ampere, the output measuring resistance or the output burden resistance is predicted to acquire a 5 volt output. So basically what we are trying to do, we are basically trying to scale down the current of 10 ampere to 5 volt. So the output voltage is 5 volt. Upon dividing with I0, we are getting 100 ohm. So the burden resistance selected here will be 100 ohm, this one. So there are some important points we should note while we are selecting the burden resistance. The output resistor or the burden resistance should not be selected beyond 150 ohm. as it introduces nonlinearity in the measurement reading. Further, low tolerance of the button resistance should be selected. Basically, a tolerance with minimum of 1% is preferred actually. And in order to increase the accuracy in measurement and reduce the effect of temperature change, so basically we can use a half watt or 1 watt power rating resistor should be selected. The current sensor circuit diagram is shown here. Here we can see the input supply required for this current sensor is plus 15 and minus 15 volt. That we will discuss in later slides, the design of these power supply, regulated power supplies. Next is the implementation of MOSFET gate driver. Basically, we are using a TLP 350 based photocoupler or optocoupler. It is basically a popular choice for gate driver application. It introduces this TLP 350 introduces an isolation in between the input side and this output side, so which helps to protect the control circuitry from voltage spike as well as noise. So basically, you can see it is a 8 LED dual inline package. So it is having 8 legs, and the input signal or the pulse basically determines the output state of the MOSFET. So in this case, when the pulse is high, when the pulse from the controller is high, so what will happen? This V supply will be pulled and the will be pulled to 15 volt, and we can see we can turn on the MOSFET. And when it is low, this ground terminal will be pulled, means it will be 0, 0 will be pulled, and the output will be in off condition, means the MOSFET will remain in the off condition. And here also it is important to note that the input is referenced to the signal ground, means here the pulse output positive will come, and this will be the negative, this will be the ground, and this will come from the signal ground or the controller ground. This will be the controller ground, and which should be separate from this power ground. By mistake, if we connect these two ground, then it will be a complete short circuit and it will lead to failure of the system. The test results of the optocoupler based IGBT MOSFET gate driver circuit is shown in figure 14. Here you can see we are getting an input pulse leveled at 5 volt from the D space, and the red waveform is at 15 volt, which is given to the MOSFET. Next is design of a plus 15 minus 15 power supply. The schematic of the DC regulated power supply is shown in figure 15. This is, I think all of you must be acquainted. I will not go in detail of this one. Here we are using 7815 linear regulator and 7915 linear regulator to generate the plus 15 volt supply as well as the minus 15 volt supply respectively. So this is the complete system developed after integrating all the components already I have discussed now. So before going to the experimental results and discussion, I would like to perform one experiment and show you the demonstration of the wind turbine emulator. For that, I have already opened my MATLAB. Basically, this block is basically the encoder interface of the wind turbine emulator. It basically reads the encoder position and the encoder delta position. Encoder delta position is basically d theta upon dt, which will represent the speed of the rotor. These two are input to this model, this subsystem, and the armature current is sensed through the multiplex channel channel number 1 of the DSpace control board. So these are the inputs to this subsystem, and the output is basically the output will be a PWM signal which will be fed to the digital to analog converter of the DSpace control board. In this, we have selected the channel number 7. So after that, first of all, I will show you the wind turbine model here. You can see this subsystem is showing the wind turbine model. Here you can see the input are wind speed, the rotor speed, the angular rotor speed of the turbine, and the pitch angle. If I open the subsystem, you can see here we are trying to compute the lambda value, that is your omega into omega turbine means angular speed of the turbine into radius of the wind turbine. We have considered 1.25. It is multiplied and it is divided by the wind velocity. So from there we are getting the lambda. That is the tip speed ratio. Next, now we are here, we are computing the lambda I. Lambda I is basically 1 upon lambda I is shown in equation number 6 of the PowerPoint file actually. So lambda I is basically 1 upon lambda I is equal to 1 upon lambda plus 0.08 beta minus 0.035 beta cube plus 1. This equation is modeled here. So basically we are having two inputs here. One is the beta and other one is the lambda, and using the mathematical function we have represented 1 upon lambda I. Here in this block, this CP, we have implemented the CP function, that is the equation 5 of the PowerPoint of the slide. I have already shown that one. So the mathematical computation is shown here. In this block, we have represented the power output of the wind turbine, basically, which is half rho into pi r square into Cp into wind speed velocity whole cube. So till this portion, you can see, till this portion, we have implemented all the static characteristics. Now next is inclusion of the dynamic characteristic. So here we have modeled the wind shear phenomena. In this we have modeled the compensating torque phenomena, and all these models are added to generate the reference torque. Reference torque is divided by the turbine constant, so to generate the reference current, for the armature. And we are considering the dynamic characteristic, and we have not considered the static characteristics. So here we have considered the dynamic characteristic, and this armature current, this reference armature current is compared with the actual armature current. So which is being sensed from the analog to digital converter of the DSpace control board. Here you can see I have taken a gain value of 20. This is basically 2 into multiplied with 10. This 2 represents the sensor gain, and this 10 is basically whenever we are sending a signal from a DSpace control board, it will be scaled down by 1/10. Suppose I am sending a 5-volt signal from the outer world into the digital domain, so it will be scaled down to 5 by 10, that is 0.5. So in order to get the actual value, we are multiplying that value 10 here. And The error of this comparator is given to a PI controller, and the after processing the error, the PI controller will generate the duty which is provided to the PWM generator block, which is set at a frequency of 5 kilohertz to generate the pulses. Again, here you can see this pulse will be generated. This pulse will be generated with a value having the high level at 1 and the lower level will be 0. So whenever this signal, this digital signal will be fed to the outer world, okay, when it will be fed to the analog domain, then it gets scaled by 10 times. So that's why I have multiplied a half here. So in the outer world, I will get the 5 volt. So this is basically about the modeling of wind turbine. Next thing, next I am trying to build the model into the display CPU. Here you can see the build process is taking place. See, we can see that successful completion of Simulink coder build procedure for the model. This one is the model name, and it is finished the real-time implementation build procedure for the same model. We can see we are getting a message that build process is completed successfully. So after the build process is completed successfully, next thing is we have to open the control desk, which I've already opened here, and we have to create a new project. So suppose I am giving the project name as STEMM session 3. And the root directory I have already made, and it is within the one folder I have created. The root directory is here. You can see that. Then I have to press next. Suppose let us give the experiment name. So we can see already the model is built. So next we will, now I have given the name of the experiment, and next then I have to press next. Then you can see various platform or
Excuse me,
devices.
sir. Excuse me, sir. Pradyumna, sir. We will take a
Yes.
15-minute break. Then we will continue the lab session.
Okay, okay.
Thank you.
Hello, good afternoon, sir. Can I hear me, sir? Hello.
Hello. If any of the participants have any questions, then you can ask it after the end of this session. Okay.
No, ma'am.
Now
After
we will
4:30,
take the
we
tea
don't
break
have.
only for 15 minutes. Then we will continue the lab session. And after the completion of this lecture, you can ask any questions.
Ma'am, please allow me I will ask one question, ma'am. After 4:30, we are not available, ma'am. Institute will be closed at 4:30, ma'am.
Okay, okay, you
Okay,
continue.
Shall I ask one question, ma'am?
yes, yes, you can ask question.
Sir, I have observed these so many papers, a PA controller, input is voltage, but getting the output is current. Input is current, output is voltage. How it is happening internally, I'm not understand. Can you explain, sir?
Once again, can you repeat
PA,
about the
PA controller, sir. PA controller. If I'm taking the difference voltages, V reference and VDC, input to the PA is voltage, but output is current. How is PA controller is changing the voltage to the current, sir?
it is basically coming. See, suppose we are controlling a converter. Okay, we are controlling a DC to DC converter. So suppose I want to regulate the output voltage of the that converter. So what I have to do? First of all, I have to bring. I will suppose I want to regulate it at 100 volt. So I will take a reference of 100 volt and I will sense the that voltage and I will try to compare it with a comparator and the output will be processed through a PI controller first. Then it will
O-
generate a current. Okay.
Okay,
So
how it
then
will
it will
generate the
generate
current?
a current. Yes, yes, that's there I'm coming.
Okay,
So
sir.
it will generate the current, and again this current or it will generate a reference current. Basically, this reference current in case of DC to DC converter is we are considering means reference current for the comparison with inductor current of the DC to DC converter. So again that current will be compared with the actual inductor current of the converter and it will be again processed through a PI controller. So it will generate the duty cycle for the converter. So you are asking that why it is generating current, why duty? That is the question, right?
No, no, sir. Actually, PA block input is voltage, PA block output is current. How,
See,
I mean, by
this is
how the parameters
see
are you are converting voltage to current? That is my question,
see
sir.
yes. If you means to do the means state space modeling of that converter of a boost converter or buck converter, if you find the transfer function. Okay, so you will
Okay.
get various transfer functions, output voltage with respect to duty, inductor current with respect to duty. From there, we are trying to implement the average current mode control. From there, you can determine various transfer functions. That's why if you clearly look into the loops, then you can see that this transfer function will appear. So, so that's why these things are coming.
So by using these transfer function, we can get voltage also output, PI output also.
No, 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 no. See, if
Only
this I
current
am
only
talking
output
about,
of the.
yeah, this I am talking about the dual loop control strategy. In this, we have two control loops. The outer loop will regulate the voltage of the output voltage of the converter, and the inner loop will regulate the current of the converter. Okay. So
Okay.
similarly, we have a voltage control mode also. Whatever I have told now is related to the average current mode control. There is another control, that is the voltage control mode, in which only there will be no current control. Okay, only we will
Okay.
try to compare the output voltage of the converter with the actual reference voltage of the, suppose we have set 48 volt or 100 volt, right? So that
Okay.
will be compared with the output voltage of the converter and it will be processed through a PI controller. Okay, then the output will be directly, here you will get duty. Okay, that will be
Okay.
fed to the switch of the DC to DC converter. So in this case, we are
So
not
through
trying to
PWM, we are
control
sending.
through PWM we are sending. So in this case, we are not trying to control the current. So that current flow from the input to the output side will only depend upon the load. As per the load demand, the current will flow through the converter circuit, and this but the output voltage will be regulated at the fixed value, whatever we have set, either it is the 48 volt or 100 volt. So basically, for your doubt, you have to go through the state space averaging of these DC to DC converters. Okay. Then you have
Okay,
to
sir.
do the small signal stability analysis. Then you have to go through some basics of control system. Then you can clearly understand. Hopefully, I have resolved your query.
Thank you, sir.
Okay,
Thanks.
thank you.
Thank you.
Okay, now we'll take a 10-minute tea break. Then we'll continue the lab session.
Good afternoon, ma'am. Hello. Is there anybody?
Yes, sir, you are audible.
Ma'am, could you start the sessions tomorrow onwards at 3 o'clock, ma'am?
Just
Because
repeat.
we are missing the main presentation, ma'am. If you start at 3:30, all institute will close 4:30, ma'am. Actually, we joined it because of the as per schedule. You are given the 3 o'clock only, ma'am.
Actually, we want to start at 3 o'clock. The only problem is very poor attendance at that time. That's why we are shifting maybe half an hour. That's why.
Okay, sir.
Very
Oh,
poor attendance at that time.
okay,
And in
sir.
the
Okay, sir.
morning 9 also same thing happens.
Morning also we are not possible, sir. At 9:30 only
So
we
so
went to, sir.
morning
Yeah.
morning 9 also very poor attendance.
Yeah, okay,
And
sir.
at 3 o'clock afternoon very poor. That's why we are shifting maybe half an hour.
Thing
So
is, we are missing a session, sir. That is why we are asking, requesting, sir. At
okay,
evening, at least it's possible.
tomorrow's afternoon session if will start around 3:15. Is that okay?
Okay, sir. Right,
Because
sir.
because
Thank you,
very
sir.
poor attendance around 3 o'clock.
Okay, I understand, sir.
Okay,
Thank you.
okay. So we'll try
Thank.
to start by 3:15 tomorrow, second half, means
Okay,
afternoon
sir.
session.
Yes, sir. Thank you, sir.
Okay, okay. Thank you.
Thank you, sir. Mm.
Okay, now we will resume this session. Now it is over to you, Pradyumna sir.
Thank you, Anindya. So let us have a recap of what we have discussed till now. First of all, we have modeled the wind turbine, and we have collected all the information required from the plant side. That is our um, data of the means the armature current. Then we have modeled everything. Then we have to build the model. Then after that, we have to open the control desk. And first of all, we have to give the some name of the project, and it will be saved in a root directory that I've already created. And next, I have to name the experiment. Next, I have to select the platform. So basically, we have a lot of display platforms over here. In my setup, DS1103 PPC controller board is interfaced, and that's why I have selected this one. And then I have to press next. Here, I have to import the SDF file. After building and after the completion of build process successfully, there will this DSpace control desk will generate a SDF file that will be stored in the folder in the root directory. So that I am going to import here. So basically, this is the root directory. You can see the name Wind Emulator STEMM 2023.sdf. It was created at time 4:19 p.m. and on this date. And we have to open this one. Then we have to press finish button. So this is the main layout for the project we have created. Here you can see on the left hand side, you can get all the project details for this model. Then we have the measurement configuration for recording the data while performing the real-time implementation. This is basically the bus navigator. Then we have a layout navigator. Then we have an instrument navigator. These things I will tell. So first of all, you can see in this tab, you can see variables are there. So this is basically our SDF file that is loaded over here. So if I drop down, so then we can see there will be a model root. So first of all, I will select using the drop down menu. Again, I will see go into the model root. So then I will enter the wind emulator folder, means into the wind emulator. Then I will bring the, first of all, I will bring the wind speed. So first of all, for the wind speed, you can see I can use the display button. Here we have a display that will display the real-time value of the wind speed. Also for real-time or for changing the wind speed in real time, I will use another block. That is basically I will use a numeric input. I'm using a numeric input, and I will right click on this and go to the instrument properties. Then on the right side, you can show the instrument property of this block. This block is coming here. You can see in the numeric input section, you can put using the drop down menu. Once again, you have to check, you have to make use variable range unchecked. Then I will range minimum for the wind turbine emulator. I'm keeping the range minimum wind speed as 5.5 meter per second and the range maximum as 7 meter per second. So using this one, I can vary my wind speed from 5.5 to 7 meter per second. Next, I will bring the measured armature current. Here you can see this will be, I'm using the display button to show you the measured armature current over here. Next, I will bring the armature reference current. So this will show our measured armature current and this will show our reference armature current. So these two should track each other. Next, I will bring the power output of the wind turbine. Next, I will bring the angular velocity of the turbine rotor. So these are the things we want to check. We will check the tracking of armature current with the reference. We will check the turbine power and angular velocity of the turbine rotor. We will see here. So this will allow, this display button will show us what is happening in real time. The value will change if I change the wind speed. So this everything will happen in real time. Next, suppose we want to see the plot. Then for that we have to use the time plotter. Suppose I want to see the IA measured and the IA reference tracking in real time. So I will bring a time plotter. So this is our time plotter, which is used to plot the data selected with respect to the time. So here we have a, next I will bring, first of all, I will bring the armature reference current over here. So you can see that we have two numbers of data over here that will be shown here. One is red, that one is the armature measured current, and green one is the reference current. So from this drop down menu, I can make the time plotter setting to continuous mode, or I can make it in a triggered mode. So let us keep it in triggered mode. Sorry, let us keep it in continuous mode. So after doing all these things, you have to press go online. You can see the wind speed is coming 6.5 meter per second. Okay, why this is coming 6.5 meter per second? Because in the mathematical modeling, whatever we have done, I have used a constant of 6.5. Here you can see I have used a constant block 6.5 here. That's why this one is getting reflected in the control disk. Suppose now I want to change this one to 5.5 meter per second. Let us try to change this value to 5.5. Whether it is changing or not, we will see. So you can see now the real-time wind speed is changed to 5.5 meter per second. Suppose let us check another time, 7. So you can see this wind speed value is changing. So let us keep it at the original state, 6.5 meter per second. Okay. Before doing this experiment, I would like all of you to see the experimental setup first. Then we will come back again here to the control desk. So for that, now I have to unshare my screen now. This is the complete experimental setup. Okay. So one by one, I will introduce you with everything. So this yellow box is basically the power supply for the field of the DC motor. This variac is used for providing power supply to the armature of the DC motor, but since it is a AC supply, what we have done basically, we have we are basically converting it into the DC value. From here, we are supplying it to the armature of the DC motor. So now I will introduce you with the DC motor and STIG set. Here you can see this blue is the DC motor and this silver color is the self-excited induction generator. This one is the field resistance for the of the DC motor. The first ammeter is measuring the field current. You can see the field current is set at the rated value, that is around 0.3 ampere. The second ammeter is kept for measuring the armature current, for visualizing the armature current in real time. Next, I will introduce you with the power MOSFET. Here you can see this is our power MOSFET. This is our power MOSFET IRFP 460, and this one is the gate driver of the MOSFET. This one is the armature current sensor. This one. Here we have the ultra fast recovery diode. This one is my ultra fast recovery diode, MUR 460 diode. And this one is our important friend, that is this bypass switch. Very important. For the time being, it is kept in open position. Sorry, it is kept in on position, means it is sorted. First of all, it will be in on position. Then, as the motor gains some speed, then we will make it off manually. And this one is our excitation capacitor connected to the terminals of the self-excited induction generator. And the power output of the self-excited induction generator is fed to a three-phase rectifier. It is within this converter. Within this converter, we have a three-phase rectifier, that is MDS 1600 by 100. That is 16 by 100. That is basically 1600 volt and 100 ampere rectifier. This black switch you can see, and the output is connected to the load box. Here, this one is the load box. This one is my load box, and I have set the resistance at 24 ohm, and it is connected to the system. You can see here it is as it is in on condition. Now let us go back to the control desk once again. Now I will start sharing my screen. Now I am sharing my entire screen. See, now we are back to the control desk. Now I am going to start the experiment. So first of all, I am applying the voltage around half the rated voltage of the DC motor at the DC motor terminal.
Sir, you are not audible. Hello, sir, you are not audible.
Am I audible now?
Yes, you are audible.
Yes, you are
Continue.
audible.
Okay. I am stopping the machine once again. Once again, I have to perform the experiment. Now I have applied the half the rated voltage. Now I am turning off the bypass switch. Now I applied the full rated voltage, that is 220 volt at the DC motor terminal, and you can see the power output. Power output of the wind turbine is 300 watt, and the omega actual is around 50 radian per second. So here you can see the armature current is tracking the reference current. So which justifies basically the emulation of the wind turbine using a separately excited DC motor. Now I have stopped the machine. Now after this, I am going to explain the experimental result section which we have left earlier. So at first, the wind turbine emulator with self-excited induction generator is tested for no load condition at different wind speed, considering only the static turbine characteristic. You can see here the wind speed is changed from 6 to 6.5 meter per second, and again it is decreased to 6.25 meter per second at around 8.2 seconds. And the corresponding armature and the measured armature current and the reference current is tracking tracking properly, and the corresponding turbine power, shaft speed are shown in figure B and D respectively. So we can see here that the measured armature current tracks the reference for all wind speed variation. And as the turbine power is directly proportional to the cube of the wind speed, it varies accordingly with the shaft speed. So now I'm going to explain about the experimental results for no load condition, including the dynamic characteristics. So here we have included the effect of wind shear and tower shadow with variation of wind speed as well. So all the waveforms are presented above are similar to the previous result. However, you can see the torque oscillation has increased due to presence of shear torque, and it is also reflected in the armature current. And the shear torque ripple shown in figure F remains constant irrespective of the wind speed variation. Then to test the system under loaded condition, what we have done, we have basically connected a DC resistive load of 100 ohm and through a three-phase bridge rectifier, and we have closed the switch. And we can see with load and wind speed change, same waveforms are observed. But it is seen that after connecting the load, the armature current, turbine power, and turbine torque increases, but with a decrease in the shaft speed. You can see here there will be a decrease in the shaft speed. Further, the effect of random load variation is observed by gradually varying the resistance from or the load resistance from 40 ohm to 20 ohm. So at a constant, this condition is observed with a constant wind speed of 7 meter per second. The measured armature and the reference current along with the corresponding turbine power, torque and speed are provided here. You can see. So we can see that measured armature current is tracking properly with the reference current, and this basically ensures the tracking behavior of armature current is found to be satisfactory, also with the arbitrary change in load. So now I will conclude my session. So what we have done today, till now we have discussed about various different wind turbine characteristics are imitated by using the armature current control DC motor as a wind turbine emulator. And the functionality of the wind energy conversion system is verified under varied wind speed condition and load condition. The results are analyzed considering the static as well as the dynamic characteristic, along with including the inertia compensation and the shear torque. And this developed test bench can have a great benefit for the researchers as well as students to study the real wind turbine characteristic and implement various control techniques on wind energy conversion system. The electricity generated by this can be used as a renewable energy input for a microgrid based sustainable educational demonstration project to aid the teaching and research on microgrid. And the power level can also be scaled up for a real implementation of a microgrid using the wind turbine emulator. So these are the references we have followed. So for better understanding, you can follow these three references. Following these three references, you can design a wind turbine emulator on your own. So I would recommend this first, second, and third for all of you to read. And these reference number 6, 7, 8, 9, 10 are basically the data sheets related to the hardware components that have been used in the setup. So I have also prepared some questions for your self-assessment. So these following questions can be used for your self-assessment as well as useful for those who want to carry out some research in the wind energy side. And so I would like all of you to note these questions if possible, or the PowerPoint presentation PPT will be shared with you. So thank you all.
If any questions, you can ask. Okay, we sincerely want to express our gratitude to Mr. Pradyumna Kumar Behera for this hardware implementation in lab setup for wind emulator, and we truly appreciate your time and your effort to give us some knowledge regarding this topic. Thank you so much, sir, and thank you, ma'am. Then tomorrow the session will be started at 9 a.m. by Professor S. Gopal Krishna from NIT Rourkela on the topic direct power control of active front-end rectifiers. Now we conclude this today's session with this. Thank you all.
Thank you, Anindya.